ChatGPT is all the rage, but it's actually just a relatively tiny increment of a larger class of algorithms that have existed for quite a while. So what I am about to say here relates to a lot of those advanced models. It will hopefully help you think about GPT, Google Bard, and all of these other magic robots in a more systematic way, and basically understand what you can reasonably expect from them, and what, on the other hand, they will never do. So what is ChatGPT? What does just the word stand for? The chat part is that it's about communication, about dialogue. It keeps more context of a conversation in its sort of memory. It remembers more from prior interactions with users than previous models. The G is for generative. All the recent craze, all the advancements that we've been seeing in these past years are based on generative approaches. So BERT, DALL-E, Whisper, and GPT are about generating new instances of data. A prior craze, kind of 5 to 7 years ago, was about more discriminative models. Discriminative means they discriminate between different kinds of data instances. They just label an example. A classifier, for instance, a tool that assigns a category to an input text, normally is a discriminative model. It just labels, puts a label on an example. A generative model, on the other hand, can generate new data instances. In the case of GPT, it would be text. In the case of DALL-E, it would be images. In the case of Whisper, again, it would be text, but based on signal, based on waveforms. So it determines the likelihood of an example rather than the likelihood of a label, and it creates the example based on that likelihood. The P is for pre-trained. These models have been pre-trained with a view of the world, if you will. They have been trained on a large body of texts, of different input texts from publicly available sources and some internal sources, and they can therefore be used for different use cases. That's what is called task agnostic. They can be used for very different tasks, but they can also be fine-tuned using more training data, and they need to be fine-tuned in order to be really, really good at something for specific tasks. So GPT is pre-trained using a huge library of text documents. And the T is for transformer, which is a type of deep learning model that is used here. And that model solves a lot of the problems we had with prior neural network approaches. ChatGPT itself is really not that unique or particularly new or even all that advanced. Here are just a few examples of so-called large language models that were released since 2018. Well, it's actually large language models and some other models that are related to them. So, for instance, the company OpenAI, which released ChatGPT, they have released several versions of GPT since 2018. They have released 2 versions of DALL-E, image generation AI, and they've released Whisper, among other things. Google or its subsidiary DeepMind have released BERT, T5, Lambda, which are also all large language models. And they have also released things like AlphaFold, which is a very specific model for protein folding. As can be seen from this overview, there's relatively little work from universities, from academia. And I think that's because the resources involved in collecting the training data and actually creating the models are immense, because these models are now so large. So I think that explains the relatively few academic contributions. Bloom is a model that has been created by a group of researchers on a supercomputer in Paris. And Wu Dao is another example that has been created by a university in China and has some very unique properties. So what is actually advancing? Basically, new models tend to be different in the underlying architecture that they use. There are many different ways to prepare the training data, to encode the input, and also different ways to apply and use transformers and the specific mechanisms contained in transformers. And it is fair to say that we are currently in a phase where all possible combinations of these options are tried out for different use cases and tested against each other in relatively quick succession. Hardware improvements and the advancement of underlying software allow for giant steps in the number of parameters from model to model. The parameter count is basically a measurement of the complexity of the model, the number, if you will, the number of connections it can make in its neural network. And as you can see from this chart, we have generally a trend towards bigger models. However, bigger is not really always better, and you can see that Wudao, an academic model from China, sits at 1 trillion parameters, while all GPT versions since GPT-3 hover around the 100 billion mark. So bigger is not always better, and higher parameter counts also require even more data to train. The scale on this chart is logarithmic, so Wudao, as you can see, is kind of 10 times bigger than GPT-3. As I said, the more parameters, the more training data required. So GPT-3, for instance, was trained on a data set that contains over 500 billion tokens. That is really massive. That contains web pages from the Common Crawl to Wikipedia to books, really all different types of inputs and documents. And that's why training cost for current models is actually in the millions of dollars, and training times is in the month on supercomputers or large clusters. So basically, if a small company claims to use proprietary AI, as they sometimes do, that either refers to fine-tuning prompting one of these existing models, or it's most likely not using large language models at all. So what are language models? They're actually a very old concept, at least from the 80s, with very different implementations. Any language model, large or not, is basically a representation of word sequence probabilities. So basically answers the question, what words are more connected than others? So given an input word, what is the next most likely word in the sequence? Hence, a language model, given the input to be or, would most likely output not. And if that result is then again fed into the model, it would step by step unveil the famous Shakespeare quote, 1 token at a time. To be or not, to be or not to be. So these days, we call them large language models. So what is large about them? Actually, everything, really. Algorithmic complexity is large. Training data is large. As we've seen before, hardware requirements are large. Processing time is large. Model size is large, and often, unfortunately, also the answer latency. And these models, being so large, are task agnostic. That means they can solve many different natural language processing tasks as long as that task can be phrased as a text continuation problem. So what would be a text continuation problem? Well, it would be, for instance, giving an answer to a question or deriving a summary for a text or writing an article based on the first paragraph. All of those are instances of models continuing an input text. This class of models really is a game changer in several different ways, but most prominently, these models can now actually generate flawless human language without actually understanding the input or the output. And that hasn't been the case with prior language models, definitely not. So what's the secret? What are the secret ingredients in the current models? So one of them is relatively old. Word embeddings are an approach to allow for the simulation of relationships between words. So basically, by using a mathematical representation of a word, by using a vector-based representation of a word, we sort of simulate a semantic concept behind it. But this approach can also create false bridges between unrelated concepts. So sometimes a word embedding will make two words seem semantically related when in fact they're not, which will reflect in the output. The second new development is the huge training data. We've mentioned that several times, but due to the size and the mix of that data, it now covers a lot of the world's knowledge in multiple languages, and that's really important. That's a huge difference to prior language models or other models. We have inherent in the model, we have a lot of facts, a lot of knowledge that the model can derive from. And then the third, as I mentioned, we're using transformers now, and transformers solve a lot of the problems that prior deep learning approaches had. They're doing that primarily using a mechanism called attention. We won't go into the specifics here, but suffice it to say that transformers have enabled us to really leap forward in several different fields of AI. Important to understand, even though it draws from the world's knowledge, it is still a language model. That means all it does is really just calculating a likely token continuation. That's all there is to it. Since these models are task agnostic, they are good at everything or nothing, depending on how you look at it. But there are different approaches for making them better at certain tasks. Most of them can be fine-tuned with more specific data. That means we basically use one of these pre-trained models, one of these general purpose models, feed it very specific input for a particular type of problem, and that makes them better at this particular task, and also decreases the likelihood of them outputting something completely unrelated. Codex, for instance, is a model that has been retuned, fine-tuned, retrained, whatever you want to call that, to output code. It's basically GPT-3, but it has been refined to generally answer in code snippets. We can also influence what the model outputs by what we ask it. And that doesn't only pertain to the explicit question that we ask it, but it can also be influenced by something like a hidden prompt. So a hidden prompt is something that is prefixed to the user's input. For instance, if I have a model and it's available to my end users and they can ask it questions, for instance, summarize this piece of text or give me a list of recommendations or something like that, we can prefix that user question with a hidden prompt to give the model more guidance. For instance, something like always answer with a list, or the following is a scientific article about biology. Or we can even go so far as to give examples of the correct output as part of the input. So when we tell the model to create a tagline for an ice cream, we can give examples of proper taglines for other products. And then the third very important way we can influence the model on the input side is obviously how we phrase the actual prompt, how we describe the task, how we ask a question optimally so that the answer will fit the purpose. By phrasing questions differently, we can actually nudge and bias the model in many different ways. So the answers to seemingly very related questions might be very different. That actually already brings us to the problems that persist or actually appeared with these models. First and foremost, the output is unpredictable and varying. So if you ask GPT-3 or 3.5 to summarize the text, it will come up with a different summary each time you ask it again. The second is, and that also influences the first problem, it has no actual language understanding. As I said, it's all about token probabilities. But because these models seem so smart, it is even more disappointing when they do dumb things. But the reality is, it's all about token probabilities. That's why it's natural that Bing's AI-driven search or BART, Google's AI search extension, they would and will make factual errors left and right. But they will always answer using immaculate grammar and vocabulary. Truth and facts are simply not concepts in these models. A truth-like answer is only given because it's the most likely continuation of the input. But that doesn't always have to be the case. On top of not having actual knowledge, it doesn't have current knowledge. So BART, for instance, is trying to solve that by linking the search engine database into these models. But up to now, the model can only emit tokens based on the data that it's been trained on. So in the case of ChatGPT, that data ends in 2021. When we try to coerce the model to discuss events that happened later, it will either admit defeat or, much worse, it will start hallucinating non-facts. As you might have noticed when playing with ChatGPT, these models are also comparatively slow. That's simply because they are so complex and huge. That's generally not a problem when a human's in conversation with the AI, but when I want to apply some language model-driven processing to 20 million documents, for instance in digital forensics or in data breach analysis, the latency might be a showstopper. We simply can't process as much data as fast as necessary for some of these use cases. Generally, these models create a potential data privacy nightmare on two sides. First of all, they ingest all this training data. They anonymize a lot of the input, and that seems to work pretty well, but there is a chance that intellectual property that is available in the training data leaks through into an answer without being marked as proprietary or as copyrighted. On the other hand, when you feed it inputs or when you feed it documents for fine-tuning, that data might also be used to retrain the model or might be looked at by analysts. Because, for instance, OpenAI, and it's in their terms of service, they reserve pretty vast permissions to use all data that you feed it for their own purposes. It's also definitely creating a copyright nightmare, because the generated language in an output of the model is always in some way derivative of the training data. But it's obviously not, or very rarely, a direct quote. So who has the copyright for what here? If the model answers based on the training data that it was given, where's the copyright? But most of the time, and kind of with almost all of these models, we can't even attribute an answer to a specific piece of text from the input data. So it's very hard to trace these kinds of matters. And we still have to come up with a legal framework to even deal with that. And as an extension of the kind of the problems that derive from using the input data so liberally, there's also a problem that I call the slow suicide problem. What happens if more and more of the training material of these models has actually been generated by the AI itself? So if these models are successful, they will replace a certain level of copywriting job. That means on the internet, there will be more and more data, more and more text that have actually been written by an AI. So now if we take that same data to train another AI on, it's sort of a vicious circle of degrading quality. And now on top of that, when we are combining search results with chatbots and actually no longer display search results, people might actually no longer be motivated to even create content at all, because if a chatbot gives you the right answer based on a document that it ingested, you never click through to the actual original document, so you never reward its creator for having created that piece of information. So it might happen that people just stop doing that, thereby starving the model of its training data. So keeping that in mind, there are still a lot of worthwhile and exciting applications that we can create based on these models. It's really the opportunities, the possibilities are boundless. First and foremost, what comes to mind is obviously chat interfaces of all sorts. Many websites apply chatbots to filter through customer support cases. Many companies have chat interfaces in their hotlines. All of these interfaces can actually become much more useful and much more powerful by drawing from this technology. So I'm actually looking forward to the telephone hotlines becoming much more intelligent and much more focused. Also, anything that is really dealing with derivative text, be that summaries, be that explanation for different levels of understanding, kind of for explain this to me for a fifth grader, be that generating questions that verify comprehension of a text, or be those actually reading materials for, I'm going to say, doctors' waiting rooms. Basically anything that is derivative of some larger article, but it has been rewritten for being more entertaining or being shorter or fitting into a magazine. Many of those things lend themselves very well to being co-written by an AI. Again, because of the fact-checking problems, the truthfulness problem, a human will always have to be in the loop in these cases, but the grunt work of the copywriting can be done by the AI. Another vast field is kind of any type of recommendation and advice bot. So for product recommendations, for instance, we tend to use collaborative filtering or some form of collaborative filtering, which basically means I will get recommendations based on what other people bought. But a large language model can actually give a totally different type of recommendation. So if you think about books, a large language model can both ingest reviews of a book and also book texts and deliver recommendations based on the actual content of both of these inputs. So while Amazon will currently give me books that are related by preference to the books that I've read, it might eventually allow me to ask something like, I finished reading the last Harry Potter book. What can I read now that is a little more lighthearted, but still fantasy and has less wizards, but more dragons or something like that? And it will most likely come up with a decent list of recommendations for this particular question. So any type of recommendation is really conceivable here, like product recommendations, recommendations about career choice, recommendations about like a studying guide. As long as the model has appropriate training and refinement data available, these applications, I think, will generally work very well. And then as a sub application of the copywriting case, I think specifically in content marketing and SEO, where a lot of the text that is being generated is highly derivative, is highly built around keywords, and is not that innovative and creative, I think any type of artificial intelligence writing support will have a huge impact there. And we are already seeing that. We are seeing AI creating keyword targeting content articles. We see AI creating social media posts about these articles. So there will probably be even more of a flood of SEO purposed and kind of clickbaiting, if you will, articles than we are already seeing. Again, because of the problems that we have just gone through, there can never be, at this point, a use case where truth is important but cannot be verified by a human. So for instance, I don't see any applications having any success, at least, where the AI would do research for me and just present the facts from a number of books, because I can never be sure that those facts are actually in the books, because it will generate stuff that is not even there, or actually truthful or actually factual. So in terms of future developments, I mean, we're currently seeing Google and Microsoft competing a little bit in the space of combining chatbots or chat interfaces with search results. Both of them are trying to make the search better by using large language models, and they are trying to solve the truthfulness issue and the recency issue at the same time. Currently, both are failing, at least from what we're seeing so far. There's a lot of garbage being output, and there's a lot of problems in these. There are a lot of problems in these applications. That might mean that they will eventually just put a disclaimer on the results, or that might mean that they will actually come up with a smarter way to fact check the output of the chatbots. We will see about that. They will definitely create content attribution, sort of a content creation problem, as I mentioned before. And I'm really interested to see how that will play out. Going larger, just from a model perspective, will still be a driving factor for a while, but I believe this is in the process of capping out, which was a little visible also in the chart that I've shown earlier. There's definitely still an ongoing battle of the model architectures, where companies are trying different permutations of approaches, different ways to treat the data. And this battle can really only benefit everyone, because it's really a shootout of what works best. I think it's obvious that Microsoft will drive integrations of OpenAI technology in all of their products, Bing, Teams, and so on. They're already on that. And now that they've invested even more into the company, OpenAI, they will definitely want to benefit from that. And Google and DeepMind on that level and OpenAI are going to inspire each other, I think, or compete with each other and kind of incentivize each other to get better for quite a while as well. Because I don't believe we're anywhere near the end of the development of these types of models and applications. And finally, on a personal note, as a company, we at Neomo, we are already using proven and customizable models such as T5 for commercial applications. We've been doing so for several years. And those applications were really unthinkable if I think back even 7 years ago. So the new models will, for companies like ours, enable even wilder applications, provided we always keep an eye on what they actually are and what we can and cannot expect from them.